Good afternoon. Hope everyone had a good lunch and that it wasn't too soporific. I will try and be perky enough to keep you awake through the early afternoon phase and the lagging, but I have some Pepsi here if anyone really needs to jump up and get some extra caffeine. My name is Martyn Lovell. I currently development manage the Windows Runtime team, which is the part of the Windows team that owns the new Windows platform we have for Windows 8. I'll talk more about that in a moment. I've been at Microsoft for about 16 years. I spent about the first 11 of them in developer division in various ways. I worked on the IDE, on debugging, on source control, on C++ libraries. And in a comment that really makes most sense for this audience, once the compiler team let me make a one-line bug fix to the compiler. So I also worked on the language, right? But really, I've been a platforms and libraries guy for a long time. And a few years ago, I moved to Windows and worked on platform here. And in this version of Windows, we're really bringing forward a whole new platform for building a new class of applications. And that platform works well with a really large range of languages, and we'd like that to be an even larger range of languages. So I'm really here to talk to you about that platform and how it might relate to what you guys do on a day-to-day basis. And I have a clicker, which makes you feel extremely managerial, so I'm going to use the clicker rather than press the space bar. That was exciting. It excited me anyway. Okay, let's start with what is the Windows Runtime. So it's a solid, efficient foundation for building great Metro-style apps. How many folks had heard about the Windows Runtime before they came to this room today? Show of hands. And how many people think they know what it is? Less hands. That's good. That's what we're looking for. So I'm going to recap first a set of material that will be familiar if you've watched my talk from the Build conference, but I think most of you are busy adding type-safe closures to unusual languages, and so probably haven't yet watched that talk yet, so I'm going to try and fill you in on the gaps. The second half of this talk will be more new to everyone, as it's specifically about the language world. So in Windows 8, we have these new, immersive, highly fluid, highly responsive apps. They're designed to work well on your desktop, work well on your laptop, work well on a Slate or other form factor of PC, and they're designed to work in a level of visual richness that we haven't yet done a great job of delivering on the Windows platform. Most of you are probably pretty familiar with the Windows platform as it is, with the Office apps, with the Windows desktop itself, and those are good systems, but we really haven't gotten that really high, visual rich, interactive platform in our world today, and we wanted to bring forward a new level of exciting responsive platform with exciting responsive UI. And it turned out when we really thought about that problem went all the way down to the OS, the API, the programming language, the kernel level. And so while I know most of you get kind of scared when someone at the start of their talk says fast, rich, interactive UI, and you immediately start doing mail on your laptops because that seems like the kind of thing you don't want to know about. It turns out that to get a fast, rich, interactive platform visually in the Windows 8 operating system, we had to do changes very deep down in the system. And I live kind of deep down in the system where the basement dwellers live, and I had to make a set of changes in our platform that would rise all the way up to the UI and enable something to happen. So because the way that you would build a great app for Windows 8 depends on programming language features, OS features, and features that go very, very deep. And that's really what I'm going to talk about today. Okay. These features make it easy to build these Metro-style apps. And a Metro-style app is not an app you run when you're riding the subway. Obviously, that's one possibility. But Metro-style is our name for a new visual look for Windows. And you can see some great talks online about what Metro-style means and how it makes your apps look. To your extreme delight, I am not going to talk about that today. But just imagine there's a really attractive kind of app that you personally don't know anything about yet. And later, you'll watch a video online. Along with these new attractive Metro-style apps, we wanted to make dramatic improvements to the developer experience. Really, I first wrote a Windows program in about maybe 1988, even though I was a Mac user at the time. And the developer experience of writing a straight Windows program didn't dramatically move forward much in that time. We actually got .NET, which actually dramatically improved the developer experience. It wasn't available to all kinds of programming languages. And so we wanted, with this release of Windows, to have a complete freedom of choice in that you could choose any language, use any kind of libraries, and use any kind of markup. In particular, we have a couple of markups we really quite like, and use that choice of all those things to enable a new generation of fast, fluid, responsive apps. I promise I will stop talking about UI very, very soon. There'll even be code eventually. I pressed the spacebar just to, well, no, that's weird. Spacebar doesn't work. Now I'm completely disconcerted. Okay, so this thing called the Windows Runtime. It's a new API platform for Windows 8. What are the design principles? We actually started from the design principles for this before we built the software, so we did that in the right order rather than the other way around. And in fact, this slide is only slightly modified from a slide that I presented to the senior leadership in Windows about a year and 3/4 ago, year and a half ago, something like that. So we wanted not only to make a major improvement to developer experience, get great IntelliSense for the Windows API, which we hadn't had, great tooling for that API. We wanted native apps, managed apps, dynamic apps to all be first-class citizens. Each of our previous attempts at doing this had kind of marginalized some part of the programming language community, and we felt that that had marginalized our ability to talk to as many customers as possible. We knew that there were tons of folks out there in the web world doing JavaScript, doing HTML, so we wanted to reach out to the dynamic language world. And we knew there were tons of people out there in the C++ universe doing native code who we hadn't properly reached with .NET. So we wanted to reach out to all these people. There's some unique facet of our lives at Microsoft that are not quite like your lives. And that's not that we go to work in the Death Star or something like that. It's that we have a platform that we version. In a curious twist of fate, as well as owning the Windows runtime, my team owns something called NTVDM. Does anyone in the room know what NTVDM is? Few hands. NTVDM is the bit of Windows that runs DOS apps. Anyone like running DOS apps? You know, it's really good fun. That Doom is really still great, I hear. So we keep apps running on Windows for a very, very long time. And one of the ways we do that is by doing what we call platform-based versioning, which means that the binaries that you compiled 15 years ago still run unchanged on today's Windows. Now, that doesn't always work out perfectly, and sometimes we have to make little changes to the Windows to keep your old apps running. But intrinsically, our goal is to make the platform change underneath the applications while the applications stay the same. So when we think about the Windows runtime, we actually built that into the platform as well. Our old platform had a good model for this, but we hadn't always worked out how to bring it forward. And so we wanted to make sure this platform versioned in the way we version the Windows platform itself, which means apps keep running, and we use simple low-level constructs that are understandable, that we understand how to version from year to 5 years to 10 years to 15 years out. Meanwhile, we wanted to build these fast, responsive, fluid apps that I keep talking about, that I promise I will stop talking about eventually. And that drove a new level of asynchronous APIs. This is really a client set of APIs. We want to build client-side apps. And a key problem with the responsiveness of our current apps, a key problem with the responsiveness of Windows as a whole, is that we don't have enough asynchronous APIs, and so people make calls to the system that do not return for a long time. Probably a few people here have experienced doing a file open in a Windows application and getting a long hand while we go to the network and the whole UI of your Windows app is hung and everything's kind of sitting there, not able to do anything. That's not a bug in Notepad or a bug in MS Paint. It's a bug in the API design of the Windows system itself, and it's a bug we're trying to fix with this iteration of the Windows platform. So we have async very, very deeply. And when I talk about what the Windows runtime means for the languages you guys work on, async will be a big part of what makes this an interesting, difficult challenge for you. Finally, we wanted well-designed and consistent objects and strategies. The current Windows platform was built up over, 25 years, and we have create window that looks this way and co-create instance that looks that way and many other shapes of APIs. And we wanted a consistent, well-designed platform so that the APIs you're using were clear and consistent. So these are our design principles. These are really the unchanged design principles from the start of the project. And in the end, we managed to deliver a platform that meets these design principles, as I will show in a moment. So when people talk about the Windows runtime, they sometimes talk about the whole totality of the Windows runtime, its ability to do networking and local storage and cloud storage and contact devices and do all these things. Windows runtime can do lots and lots of stuff. Lots and lots of stuff which I'm not interested in today. So forget this picture, which is fascinating, but which we're going to skip, and think about this picture. This is a picture that will describe how the Windows runtime relates to programming languages and how it relates to the kinds of stuff that you work on. Ultimately, at the core of Windows is something we like to call the Windows core. We're not giving degrees for our naming skills. And the Windows core is the foundation that underlies any app. Ultimately, Windows is the runtime in our system. We try to think that apps talk directly to Windows through Windows runtime because Windows runtime is the whole of Windows. It's the way that you, as an app developer, or you as a language developer, get to Windows. Now, you'll see that my slides build up one box at a time. This is how you can tell that I'm what we call in management. The combination of a non-white background color and slides that build up in the time means I probably didn't write code in the last 6 months. It's one of those correlations you want to watch for. Okay, Windows Runtime Core builds on top of the Windows core, and then these APIs that I showed you in big on the last slide build on top of that. So we have a set of Windows services, a Windows runtime that provides some basic typing and basic language features, and then some services on top of that. So how do you as a programming language relate to that? Well, every Windows API in the Windows runtime is described by some metadata. And that metadata describes exactly what the API is, what interfaces and functions and types and methods it provides, and where it fits into the namespace of Windows functionality. So when you take all these pieces of API together, the namespace and metadata provide a language, the way to create objects from the Windows runtime. And then something called the language projection, which we'll spend some time on later, is the exposure of the Windows runtime into your language. One of the principles of Windows runtime is we kept the base of the runtime pretty simple. We used basic interfaces and basic types, and we used relatively complex but easy to version protocols that mean we can keep Windows doing the same thing across multiple versions. But then we expect languages to see natural, familiar, modern views of that Windows runtime. And each language does its own projection of the Windows runtime into that language. And each language effectively generates from the metadata automatically, either at compile time, interpret time, or JIT time, a projection that exposes the Windows runtime into the language in a way that's natural. And I'll talk a little bit more about that later. But that language projection is the key step here in taking what is a relatively understandable but relatively low-level Windows API and bringing it up into each language in a way that's slightly different for that language. And of course, on top of that, you build a Windows 8 Metro-style app, which has exciting, fast, fluid graphics that you don't care about in this room. There's three components I'm not going to talk much about today. A runtime broker runs certain permission-type operations out of process from your application. The web host is the place that HTML and JavaScript apps run in the Windows 8 world, and so we run certain kinds of, we obviously have a web browser, but we also have the web host, which hosts HTML and JavaScript-based Windows 8 apps. And finally, each of your languages has its own support library. If you work in C or C++, you have something called the C Runtime Library, or CRT. If you work in JavaScript, we have a library for you called WinJS, which is obviously Windows JavaScript, not difficult to work out. And of course, if you work in C# or VB, you have the CLR helping you out too. So each language has its own support that is helping out the language. Okay. So I talked about the projection, and what ultimately we have here in the Windows runtime system is a contract. It's a contract between the app and its language, and the language provides the projection that then gives the app developer access to the Windows contracts themselves, but in a natural and familiar way for that language. So I'm going to talk about the contract and how it works. And what is a Windows runtime object? Well, a little bit of this diagram may seem a little bit familiar to you. On the top of this box, you see something called IUnknown. Who's heard of IUnknown before? Okay. Hands up if you like addref more than release. Hands up if you like release more than addref. Okay. Bit of an even bet there. Okay. IUnknown is a kind of fundamental piece of Windows from a very, very long time ago that provided the foundation for what we used to call COM objects. And IUnknown is still the same way it was before. It has addref and another API that should be called releaseref, but is called release for reasons that we can't really understand. And it has a way to query to other interfaces. So it's a very basic piece of Windows. Now, when we were building the Windows runtime, we started from a few pieces of COM as a way to bootstrap the system, and we kept IUnknown in part of our system. But what you'll find is we didn't keep many of the pieces of COM as things went on. We changed the apartment system. We changed the metadata system. We changed almost all the pieces of the system. So occasional bits survive, but it's better to think of the WinRT as a new platform that reuses a little bit of the old one than as an evolution in that sense, because there's relatively little in common. And above IUnknown is IInspectable. And so where IUnknown is effectively a known unknown, IInspectable is an unknown unknown, in that it gives you a way to dynamically inspect the type. And IInspectable is kind of at the root of our choice to unify static and dynamically typed languages. You know, IInspectable gives you access to the kind of runtime information that a classic IUnknown-based object doesn't have. We wanted to call IInspectable IKnown, but it turns out if you speak fast enough, IKnown and IUnknown sound like saying almost the same thing, so we actually had to go into IInspectable as well, which sounds rather more criminal justice-y. On the side of this object, we have, this object is about storage, so it has some interfaces, one about storage file, storage item, etc. And those are grouped together in something we call a runtime class. And that's a class you can create at runtime, so the name is not exactly weird. And a runtime class is what you might call a class. And those runtime classes are the foundations of a Windows runtime object. On the bottom of this picture, you see the activation store, which is where you create things from. It's a list of what objects we know how to create. And the metadata, which I already talked about, which is stored on disk and describes every Windows API. So a Windows runtime object is a very, very simple thing. You can get very powerful, very complicated objects, but the base level of Windows Runtime Objects is very simple. And that's important because we want Windows Runtime Objects to be implemented in multiple different languages. There isn't one fixed language that's required to do this. Any language can produce a Windows Runtime Object. All you have to know is how to write metadata, how to implement IUnknown, and how to implement IInspectable. And you're well on your way to having Windows Runtime Object. Okay, so obviously, our type system goes beyond objects. And so we have some basic types here. I think none of these basic types are going to be surprising or scary to programming languages people. I think, in fact, it would be kind of scary or surprising if anyone in this room were scary or surprised. But to run through them quickly, you've got integers, you've got strings. We have a special string type. And we have enumerations and structures. And structures contain basic types like strings, but you can't have structures containing interfaces. So there's like a structure is a pretty pod-esque kind of type, if you know what a pod is from the C world. We have arrays of basic types. Then, of course, we have interfaces and generic interfaces at a very restricted level, and runtime classes. So these are all the basic types, and this is what you might expect any simple type system consist of. There's nothing, I think, here surprising or scary. There's another level of basic stuff we have, which are patterns. So it turns out that one of the keys to our goal here is to have something like a collection in a Windows API. Say we have a collection of all the monitors you have attached to your system. How many has more than 3 monitors on their system? No one? Wow. Multi-monitor is good. I recommend it. Anyway, so we have a collection of all the monitors on your system, and we return you a collection of those monitors. Now, in C++, you'd like that collection to look very like an STL collection. You'd like to be able to call begin and end on it, and you'd like to be able to iterate it through it using ++ the same way you would with an iterator that came from STL. That's a very fundamentally natural and familiar way for a C++ person to see this collection of displays. It's also very fundamentally different from how a C# person might want to see it, with a for each and iteration that way, and again different from how a JavaScript person might want to see it. And so the projection takes these basic interfaces that are simple and well-defined and projects them up in a way that's natural for the language. And each of these patterns is a thing that we expect a language projection to think about and work out how they will appear most naturally for developers in that language. So I talked about collections. We have writable collections. We have vector view, which is a readable collection. We have maps as well as vectors. We have observable vectors, which send you events when they change. So we have a collection of collection interfaces. We have delegates, which are effectively object-bound callbacks, very simple, basic concept. We have events when we tell you when things have happened. We have property sets, which are like key-value type operations, very, very simple. And then most fundamentally, at the bottom of this slide, and we'll spend more time on this later in the presentation, we have async operations. One of our fundamental rules with the Windows Runtime is we want to not do anything on the user interface thread that will cause the user interface to block. We want the UI to be responsive as you move your finger up and down on your snazzy touch machine. You want the UI to move up and down with your finger. We want you to not get blocked when you open a file over the network, et cetera, et cetera. So we made a guideline for any operation that might ever take more than a certain number of milliseconds. We'll make into an async operation. And that means lots of things that you think of as basic in an OS, like opening a file, putting up a dialog box, etc., are modeled as async operations in the Windows Runtime, and it's a very fundamental feature. So that last thing I said is very deliberate. Putting up a dialog box like, do you want to continue? Yes, no. That's fundamentally an async operation, the way we think about it. So it's not just limited to, oh, I'm downloading a 10 megabyte zip file from Siberia, and that's an async operation, because we all know that's an async operation, but it's really limited to almost any significant operation that takes time is modeled as an async operation, which you'll find out about completion of later. And that's going to be a feature that's so important to the OS API that needs to be modeled up into the language if the language is going to do a great job of exposing the Windows runtime. And you'll therefore hear me witter on about it endlessly over the course of the presentation. Okay, let's talk about the simplest of these patterns and think about how this works. So we have collection patterns. And if your collection is like an array or like a vector, you expose like a vector and a vector view and maybe an observable vector if you want to, as well as your usual IUnknowns and IInspectables. And then if you're more like an associative collection, a map of some kind, you'll expose a map and a map view and an observable map. So again, these are interfaces, which means that if your language has a standard set of collections, imagine in your language you have your own vector and your own array and your own associative collection implemented in your language, you should simply expose these interfaces on top of your existing implementations, because we don't want your users to have to copy data from wherever it's stored in its native language place to be provided to Windows. Instead, your collections can be exposed directly up into Windows via these interfaces. And so that's, again, part of the goal here is to make an efficient set of contracts that there's no required data copying for, and you don't have to say, oh, well, I have to make another copy of this data into the Windows structure because that's like this way and I was that way. Because we used to waste a lot of performance in the classic Win32 API doing this copying over and over again. So we should be able to just put these interfaces on your collections as they are. Okay, let me talk a little bit about metadata. So the Windows metadata fully describes the Windows Runtime platform. It describes every class, every interface, every enum, everything that you can activate in the Windows Runtime is there, and it ships both in the Windows SDK in full detail and in your system in a directory that's confusingly named Win Metadata. And you'll find in that directory metadata files for every type and piece that's stored in Windows. When you ship an app, if you want to ship a Windows Runtime object that you're going to use within your app, because, for example, you could have JavaScript code calling using the Windows Runtime down in C++ code that you wrote yourself, you can generate Windows Runtime metadata directly by writing C++ or C# code, and that metadata is emitted by the compiler or by a helper tool and can be consumed by other Windows Runtime-based tools. And so Windows Runtime metadata isn't just about describing Windows. It lets you build hybrid applications that mix together one or two different programming languages through a standard set of metadata and information about that language. Now, the Windows metadata is actually in something called ECMA 335 Partition 2. Anyone ever heard of ECMA 335 Partition 2? Excellent. It's otherwise known as .NET metadata, CLI metadata. We use the same file format. We do ascribe somewhat different meanings to some of the terms because we're trying to use it to describe a low-level native platform and not a GC managed platform. But it really turns out the differences aren't as much as you might fear they could be, which means a lot of the existing tools just work either unchanged or with very minimal change. But you can browse, you can open the Win Metadata folder and use ILDASM to look at it. And if you get excited by ILDASM, that will probably be a fun thing to do after you leave this talk. And of course, the Win Metadata knows all about the patterns. It knows about async, it knows about events, it knows about delegates, it knows about collections, because it has to be rich enough to how every language we build on to project up in a natural and familiar way on top of these really basic Windows level interface. And again, the metadata is exactly what we use for IntelliSense, and so that means that IntelliSense is working on statically known information, and that statically known information, in this case, is the metadata. That's what your IntelliSense uses to understand what you're using from the Windows runtime. So the Windows metadata is a critical part of this story. I want to talk a little bit more about versioning. And I do this because I know that there are lots of different approaches to versioning, and ours is very tied to our platform versioning approach I talked about earlier. When we ship Windows current version, Windows version 8, you will ship you the metadata about all of Windows 8, and all the items in there are annotated to say they're available on Windows 8. And because this is the first version of the Windows runtime, that's all we need to say. But then, eventually, we might ship a future version of Windows. We'll call that an unnamed future version of Windows. And because we want your existing apps to run, in general, we don't remove any functionality from Windows. We just simply add stuff. And so the metadata for a future version of Windows will contain the list of interfaces that were added in that version of Windows tagged with a version number. And that lets your language think about exposing objects differently for developers who are building apps targeting both versions or apps that are only targeting one version. And we expect that lots of developers want to write what we call adaptive apps, that are apps that run both on the current version of Windows and previous versions. And you can use this metadata to make sure your language has a really good versioning understanding. And that's a really unusual point that I want to reinforce. When you think about building a language that can work on the Windows runtime, you really have to think about how Windows is going to version and how that versioning is going to expose up into your language so that your developers get an understandable experience when they move from building apps just for Windows 8 to building apps for the next version of Windows or for future versions of Windows. And so there is some language impact of versioning there, and I encourage you to think about that because it's often an ignored point. And in my personal experience, it's always good to think about V2 before you finish V1. Okay, let's talk about asynchrony, or asynchronicity, or asynchronicity. Whichever of those words is right. So asynchronous is a really basic requirement for Metro-style apps. We need them to be responsive and ready all the time. And this is where the UI that we want has driven its way all the way down into the lowest level of systems. We need those long-running APIs, and long-running to us means more than 50 milliseconds. It's a very short time to be delivered as an async API, and that makes these apps responsive. It's clearly simpler if we had simply done everything in a synchronous way, but we've tried that, and it ended up with lots of apps that hung a lot. It would also have been simpler if we just said, well, why don't we offer you both the synchronous API and the asynchronous API? But in our experience, if we offer you the synchronous API and the asynchronous API, that's like offering you the cookie and the cookie wrapped in plastic. And everyone just picks up the cookie and ignores the cookie wrapped in plastic because the cookie wrapped in plastic is more work. So in cases where we know it's necessary for system responsiveness, we are requiring use of asynchronous APIs. You obviously can write crappy code, and we assume if you write crappy code, your app will get a crappy review in the App Store. But beyond that, these APIs allow you to make sure that your app remains responsive in a wide range of situations. And so we build it directly into the API shape. Our async protocol is super low level. There's a talk online by one of my directs called Ben Kuhn, which goes into this in great detail. But the async API has get results and start and stop and lots of complicated protocol. But the languages will hide that from the user, and the user will just deal with these objects in a way that's natural for the language. And I'll talk about that a little bit more later. Let me just say that deciding how to do async in your language is one of the hardest and most challenging Windows Runtime language design decisions, and it's going to be the thing that will take you the most time. And in many cases, you'll have to think hard about how your users want to think about operations that enter the future. And each of our three languages has a significantly different approach to how to do this that fits well with their languages. And so that's really a key question for you. OK. I'm going to talk briefly about threading. In the Windows Runtime universe, there's a main UI thread in which application UI runs and runs in a single-threaded way. The way we think about that is that most UI programmers don't want to receive the onCancel button event during the processing of the onOK button event. And so those operations are single-threaded for kind of usability of the API rules. But beyond that UI, in general, all other Windows objects run in a thread pool in what we call the multi-threaded world. And each of those objects agilely works on any of those threads. And there is a lot of interesting stuff to talk about on threading. But the thing to remember here when you think about this from a language perspective is don't ignore threading up front. Think about how your objects will work. Windows Runtime objects will work on any thread in general unless they're UI. And that threading model should be something your users don't have to think about. Like, we don't want your users to have to think about this. The people writing projections, the language designers, have to think about this a little bit. But end users should not have to do so. Oh, and I just said all this stuff to the picture instead of the slide. So I'm not going to say it all over again. It was so much fun the first time. OK, there's a Windows namespace. We radically started Windows namespace with Windows dot. And so objects are under there in a simple, unified, hierarchical way. And of course, if you use IntelliSense, you can type Windows dot on your machine and see Windows.storage, Windows dot foundation, et cetera, et cetera. And so you get great IntelliSense in browsing because we're just reading the metadata and looking at the namespace. In general, there is one clear type for each function, and this is not a short-term, but also a long-term goal. We have quite a lot of video APIs in the Windows APIs, it turns out. Quite a few. I encourage you to not count them, but there's more than one. And so when you're a video developer working on Windows right now, and you want to know which API should I use, you have quite a cornucopia of choices. In the Windows Runtime world, there's one video API. It's in the right place in the namespace. You know what it is, and it's going to do video for you. And so we're trying to keep the namespace clear and simple so that there isn't a wide range of incomprehensible choices. The catalog, that is the list of APIs, is extensible, which means your apps can add Windows Runtime types, but those types are private. You can expose Windows Runtime types to allow your JavaScript code to call down to your C++ code or your C# code, but you can't expose a type to another app. Essentially, each app is a private island because we are trying to make sure that people can trust that when they install an app from the App Store, it's not going to interfere with other apps or cause problems with other apps. And so each app is its own independent island of Windows Runtime naming. This also means that you are tied to only the things you ship in your app and the things that Windows ship and nothing else. OK, so we talked a little bit about projection. Let me go into the next level of depth here. How are we on time? I think we're OK. So the big red blob that was projection in the earlier diagram is now a big black sliced rectangle. But it's doing the same job. It's taking C++, CLR, and JS, using the Windows metadata to connect up to the Windows API directly. Oops, that was one too many. And so when you think about what's happening here, each projection is looking at the metadata, deciding what the language should look like, and understanding how to project it into that language. So the projection is like a thin, efficient, automatically generated wrapper. If you've ever been in a situation with previous Windows APIs where we added an API to Windows 7, say, but it wasn't available in the runtime library that your language likes, it wasn't available in the .NET runtime library, or wasn't available in CRT, or wasn't available in some part of the system, We are trying to remove that problem because the language compiler, the language environment will automatically generate the projection from metadata. So the day that Windows ships new metadata, any language, any runtime environment can pick up those new APIs on day one and have them appear in a fully natural, fully familiar way in that programming language. So this is designed to totally cut out a cycle that happened between our developers, the tools providers, and the OS, where every developer had to wait for a tools provider to provide new tools to go with the OS that we shipped and make those things come together much more rapidly. So that's a key feature of this scheme. I feel like I talked about everything on the slide earlier in the talk when I had the picture up of projections. So I think I'm going to move forward past that one. So one key question that you might ask as a language provider is, can the Windows runtime truly be at home in each language? And the answer is yes, but it will never be perfect. Obviously, some aspects of the Windows runtime can map pretty well into almost any language and are going to be good. Object creation, doing collections, working with the naming. Like, we can actually adjust the typography. When you take a Windows runtime method into JavaScript, it becomes lowercase for its initial letter because that matches JavaScript convention and not the Windows runtime uppercase convention. And return values can work well. So there's always going to be a lot of things that will integrate well, of which this is just a few. Other things are going to be dependent on Windows. For example, if the Windows runtime has the first parameter be the return value in some set of functions, and in your language, the last parameter is always the return value, there's no way we're going to re-swizzle the parameters in the projection in order to do that. It would be too confusing when you looked up the MSDN documentation and saw that some of the parameters are in different order in different languages. I think that would just be incomprehensible. Similarly, if in your language you call a file an item, in the Windows runtime we call it a file, the API is still going to be called file. So there's going to be some impedance mismatch, just as there is when you mix different libraries in the same language, for example. So we don't think this is a key problem, but it's important to recognize that even though our goal is for the Windows runtime to be natural and familiar, it is by definition going to be limited by being a part of an API that wasn't perfectly designed for your exact language. But the way it's worked out for us in JavaScript and C# and VB and C++, we found extremely natural mappings for each of those, and so we have not found this problem. I think we'll have the most challenge with, say, functional languages where the impedance mismatch between the OS and the functional world is a little bit greater. Another thing, you should have great interop with language types, and sometimes you'll overlap with those language types. You might not want to expose the Windows runtime string type because you'll have your own string type and you just invisibly translate between those two in your projection layer. So there's always going to be some overlap because everyone's going to have a string type and there's going to be some translation that might exist in your projection depending on your language. Okay. So let's talk about what it takes to design your projection. The next 3 or 4 slides are a set of bullet points about things that we think will be interesting if you're taking a language and bringing it to, taking a language and adding Windows runtime support to it. And each one of these is a design item or an implementation item we think will be interesting and challenging, but none of these are insurmountable, and all of these we've done for several languages by now, so we think we pretty much understand how to do them for many cases. Obviously, the very basic thing, you have to map the type systems. We have a bunch of types. If we have delegates and your language doesn't have delegates, you've got to work out what a delegate looks like in your language. So you've got to understand that and think about round tripping, because remember, interfaces in the Windows runtime go in both directions. And so it could easily be that you're implementing an interface or providing an interface, or you could be consuming an interface. And so these types have to round trip in both directions in ways that remains natural and where you don't lose identity and you don't lose some kind of semantic reasonableness. We actually had some weird problems with JavaScript dates, as I remember, that we eventually fixed. Map patterns and abstractions. Ensure your collections be passed to Windows using your own collections. Don't make your users use our collections, because we don't provide collections. You provide the collections in your language. We assume everyone's already written a good collection, and so you just provide the interfaces on the collections that you already have in general. Similarly, if you have a callback model, some sort of eventing or message passing model, you want to probably fit our events and delegates into that model. Depending on how message-based you are, that could be more or less complicated, but again, it's a question to understand. And of course, think about threading and async. There's a bunch of stuff you can see in what we've already done. C++ folks did a great template library that provides amazing support for tasks and so on. The JavaScript folks use promises, and the C# folks used await. Each of those is different. Each of them is pretty cool, and each maps into the language very well. And so you want to think about exactly how future results map into your language and how you're going to deal with those and errors from them and all the issues that go with async. Harmonize object lifetime. Obviously, Windows runtime objects are really deterministic objects. You call addref, you call release. Once your releases outnumber your addrefs, the object goes away. It's extremely deterministic. Now, of course, if you're in a fully GC'd world, you might have something more complicated, something more not time specific, and you might end up needing a proxy object like the CLR does with RCWs and CCWs. That's one good approach for that we found worked very well. There are other things that can go there. We have an interface called iClosable, which is about doing something like disposing for an object at a specific moment, which is useful for things like file objects that might have a specific time limit. And so you want to think about iClosable as well. But you have to plan the shutdown of your app carefully. In some cases on the new Windows 8 world, your app is going to be shut down automatically for you because we're going to discover that there are other apps running and you're sitting in the background not doing anything. But thinking about how your app shuts down, how the lifetimes of objects work is really critical. I've talked a lot about versioning, so I'm not going to talk about that again. Errors. Windows runtime errors are simply H results, which are 32-bit integers, and they return from functions, and that's it. Unless your language is extremely unusual by modern standards, you will have exceptions in your language, and you should map every one of those H results that is a failure into an exception and throw it like an exception. That's a pretty normal pattern. We've used that across all our languages with success. But that's a key thing that happens there. And similarly, you have to work out what happens when one of your exceptions is returned back to an interface that you were passed to call back into Windows. You've got to understand how to propagate that back as an H result, give the user appropriate chance for debugging. We have some clever debugging APIs there. And so there's some things you might want to do. You've got to read and write metadata. If you're going to consume the Windows runtime, you need to read it. If you're going to let other people consume components you wrote, you've got to write metadata. We have APIs for doing those. And you've got to make sure your metadata conforms to the standards that we provide in order to be consumed by all the languages. It's possible if you go spelunking to find files on disk, but in general, when you're binding to a Windows runtime type, you should use our APIs to load metadata, our APIs to create objects, because those are the ways we can ensure that when we come out with future versions of Windows, things will keep working as they should. When you get around to implementing your projection, you will have to adjust your standard library. The Windows Metro style environment has a smaller set of APIs than the classic Win32 APIs. For example, there's no such thing as a console app in the Metro world. I think that's no surprise to anyone who understands Metro. And so you might have to adjust your standard library to remove some things that don't make sense there. You might want fprintf, but not cprintf, or some such change. You'll want to obscure types with natural analogs. Don't expose a Windows type if there's a mapping. Like we have an int32 type, but we think you should probably use your int32 type and hide our int32 type. Conversely, you probably don't want to hide our async interfaces fully. Even though you have your own async projection, you'll probably keep those interfaces out there. But you'll hide some basic types so that people can't get to them and only expose them if there are important semantic differences or if users have a need to go to the next level. So the whole deal with this projection technology is the ability to use your language projection to step above the details of the platform and provide a thin, efficient, but effective layer. Make sure your projection boundary is efficient. Don't copy strings, don't copy collections. Try to avoid copying things in general. You wouldn't believe how much overhead that adds to the system if you do that copying too much. So making that super efficient is a key part of getting this right. Okay, before I finish, I wanted to show 3 pieces of example code. And this is the same exact function implemented 3 times. It's from our samples in Windows, and this function isn't a particularly exciting function. It's about a proximity sensor and getting some requests, and it doesn't really matter. But what you'll see on this first slide is we're doing async in JavaScript, and we have a then operation because there's a JavaScript promise here, and you can see how that we're dealing with this operation with a connect async in red, and that starts an async operation, and then we look for this code to run after that async operation. Now, no one here can possibly have understood this code yet, but let me go forward to the next slide. Here's another set of code you also don't understand, but it's in C#. And here, this is exactly the same set of operations, but here we're calling await on connect async, and await, again, spins an independent operation to get that done, and then it comes back after the async operation is done. This is how C# handles this. Finally, C++, you have the concurrency task, which is a template library, and it also is connecting to an async object and waiting for the end result and then doing a then-style finish. Now, the goal of these 3 pieces of code is not to have you understand each piece of code, but to point out that this is just one simple function I took from some random sample of our code. At the OS level, exactly the same OS calls we made in these 3 pieces of code. This is the same code from the OS perspective. But from each language level, each language projection, they're doing a slightly different kind of thing that's natural and familiar in that language. And so a key part of our goal here is being met in this example and all our examples, where language programmers in each of these languages will feel comfortable, able to deal with this, and we will in turn provide a single set of OS services that work in all those languages. Okay. So ultimately, the goal of this talk is to encourage you, people who work on programming language stuff, from me, person who works on runtime stuff, to build some languages for our exciting new developer platform. Windows 8 is going to be a solid, efficient platform for building these Metro-style apps. It's going to be super commonly used, and we'll make it available. We'll give you HTML, and we'll give you XAML, we'll give you C++, we'll give you JavaScript, we'll give you C#, we'll give you VB. But you have languages too, even languages I hadn't heard of before this week. And we want you to bring your language to Windows Runtime, to create a language projection, to make it Windows a natural part of your language when running on the Windows platform. And of course, we're here to help if you need help doing that. But ultimately, we feel this information is a great starting point for doing that. Here's some follow-up information. My email address is there. I seem to have left my business cards in my car, but feel free to take my email address, and I'll try and bring the business cards to dinner as well, where we'd be happy to see you. The consumer preview of Windows is available for download. Feel free to run Windows 8. I'm running it on this laptop. It's running super well. Also on this slide, when you get the slide deck, these are some links to talks from the Build conference we ran last September. There's my talk, which of course is a thing of beauty to behold, and some talks by some other people as well. And they're on various parts of the Windows Runtime and how it fits together. I think I have 10 minutes for Q&A at least.
How much?
10 minutes for Q&A?
No, it should be, I think we have only a couple minutes actually, because it was 40 minutes.
2 minutes for Q&A.
Yeah.
Okay. Questions? Go.
That was a good.
Oh.
Sorry. Go ahead.
I do know we made a change to that. Sorry, the question is, why do we change the interface to the CLR system.type in the Windows 8 version of C#? Yes? And we had to make a number of changes to the C# to lock it down to only use a set of options that were available in the Metro-style API set, which is less. But I don't remember what the details of why we made the system type change. Send me mail, I will try and get you an answer. But I'm glad the app building went well apart from that.
I mean, the philosophy looks very much like COM. So what's changed? I mean, apart from being a completely different...
So philosophically, COM was about taking a world of different languages and using interfaces to abstract them. And we're about taking a world of different languages. So in that sense, some philosophies are similar. But if you worked with COM at the time, as I did quite a lot, there were lots of pain points to COM. There was an apartment model that was extremely hard to get used to. There were events delivered by connection point containers that had weird threading semantics and were difficult. There was a metadata format called the typelib, which was based on, I think, the VB symbol table and was super difficult. So the piece of COM that is largely unchanged with Windows Runtime is IUnknown and the marshalling and proxy system. Beyond that, almost everything you can see about the Windows Runtime is about reimagining an interface-based system. So while we kept IUnknown, because that lets us do some cool interop within our Windows code base, think of the Windows Runtime as a reapproach to the same problem with some of the same philosophical points, but some very different ones. For example, COM was horrible at IntelliSense. There was no real way to ever get good IntelliSense for a COM object, whereas we have first-class IntelliSense across the whole Windows API. So yeah, you're right. We stole some philosophy points there. There's definitely some overlap, but it's really a reimagining of all the key points.
All right, so we don't have any time for any more questions, but I'm sure Martyn will be around, and
I will be around.
He'll have his business card. So this was a very interesting talk. Thank you very much.
Thank you.